load and failures. So what we said is that we have a force that is applied to block of rock. That force is distributed across some sort of a plane, a surface, and you have a stress that is defined as the force divided by the area. You create a displacement, the deformation, that's specific strain. The more I load, the more strain I cause in my sample, up to a point where that behavior is not linear anymore. It deviates from a line, and then that path, that relationship between stress and strain will completely change, and we follow some sort of diverging path. That point is called the strength of the material. So one thing is that needs to be clear, strength is one point. Okay, don't use that in the wrong way. The strength is really the maximum stress that the rock can support without breaking. It's basically the point where you go from absolutely intact to broken piece. Okay? And the point where these start deviating, in this case more or less here, this graph, from the linear is the yielding point, like in material, is where you lose the linearity. Yes? Yes. No, because the number 3 is very, very long. So, okay. So, just to give you the way, so let's go back a little bit. With respect to the plan of lecturing that you got, I decided to sort of try to combine the first two, because the third one is really, there's so much material that 1 hour would be impossible to cover. So it sort of would be divided in blocks, as you can see here in the notes we get. But I would like to keep on flooding you with information, and then later this afternoon I will continue with I think the part that I like the most. So that I can talk for days, and I condense in 1 hour. It will be very tough. So let's. If you're okay, I would like to keep on doing that. Okay. So. One thing you need to remember is that strength and stresses are not the same. Strength is one part, and the stress is basically what is the force divided by the area at that particular location. So it's really something else. So adding to the two definitions that we gave first, before, the strength is really it's one point. It's where the rock goes from intact to and that is really a number, a value that you need to estimate. It's one number or is a range? It's a range. For metal, it's a number. For concrete, it's close to a number. For rock, it's a range. And that range is really quite large, as you will see in the lab. Any of you has ever done material testing on rock? 1, 2, 3, 4, so 5. Well, if you can, do it. Touch the rock.
Tomorrow they will do it.
Yeah, but do more. Not just to borrow for a little bit. The point is that touching the rock, feeling, and start seeing how it behaves, it will give you an amazing experience. Even though you don't do tests all day, but just when you have the occasion, break that rock. Break that rock, see how it breaks, and that will again relate those numbers, the strength, the UCS value, to the reality. And again, UCS is one value per test, but you get the same block, you get 10 different samples out, and you are going to get 10 different values. Very likely. So, talking about UCS, UCS is a uniaction compressive test or unconfined compressive test. As both terminology are UCS and actually the same thing. Uniaction means that you have only one stress, unconfined means that you don't have any confinement around. It's much the same thing. And it is one of the value, the test you always need to run to understand what is the strength of the material you're dealing with. Plus, you're going to measure a few other things. That is the strain at which it breaks. And those strains are really, really small. And also, as function of knowing the strain and the stresses, you can calculate what are the equivalent elastic parameters like the Young modulus and the concentration. That means that at the end, you generally have a curve like that. Where you always have sort of a shallow slope at the beginning, and generally that is that is where you have micro cracks and closes, so the material seems softer than what it should be. Plus, the sample preparation, the machine compliance. There's a lot of other stuff goes in that initial number one curve, that path. That personally, you should completely disregard in 99% of the tests. That is my personal opinion. And the reason is that each machine will have a different response that will actually be captured by that number one. Plus, how you set your sample, how you prepare your phases. Everything is that. There's so much uncertainties that it's pretty much impossible to actually get any reasonable interpretation of what number one could be. Number two is really the area, that section of the curve where the rock behaves linearly. And that is really where you're going to calculate your values. And generally, that is about, let's say, from 20 to 60, maybe 70% of the strength, the peak strength. That is the area where you should expect a linear behavior, and that is the area where you're going to calculate your Young modulus and Poisson ratio. And generally, the standard says that you calculate that at 50% of your peak strength. That is what is suggested. But you are going to touch this more, so I'm sort of skipping that. At some point, the rock starts to deviate, even though you don't really see it. If you start looking at the curve, it's not linear anymore. Start to deviate. That means that something is going on. It's not linear elastic anymore. Is probably start to fracture a little bit, micro cracks, and you can actually hear them. Put a very high sensitive microphone there, so you start recording what is called the acoustic emissions, small cracks that are nothing else than a sign that the rock is start to feel the load, feel the stress, and break. So that will make your sample a little bit softer up to a point where actually the process will start to accelerate and will reach a peak, and after that will fail. And how it fails will tell you if the rock fails brittle, in a brittle way, so in an abrupt way, very dangerous, or in a more soft manner. And that means that it's really it's a more plastic response. It's a soft. And then at some point the rock tends to reach sort of a residual state, that is the residual strength that the rock still have, because when it fractures, it's not a nice final fracture, has some waviness, some asperity, some roughness, and that roughness is helping you to not completely disintegrate and fail along that particular plane. Okay? And the residual state of your rock mass. And that is really what you are looking for in mining. So in mining, you have two things, especially in hard rock mining, that we want to avoid. One is the brittle failure, because that is abrupt and release energy, too much energy that could actually kill you. I'm not joking, kill you. And the residual state is where fracture happened, and the rock is sort of there, it's fractured, but it's quiet, doesn't explode anymore. But that is really what you want to use. Generally, you want to use that because it's safe. Okay? So fractures can become your enemy, or you can make out of the enemy your best friend. Okay? At the end, what is going on is this type of condition. Okay? Now, you're going to do a few tests. And, oh, by the way, I'm extremely opinionated, and I think you will learn about me in that sense. I have strong opinions about many different aspects of the rock mechanics. And one of the things that you need to pay extremely attention as an engineer, and that is why I strongly advise you to do rock mechanics test, material testing yourself, to gain an experience, because you need to be able to distinguish rubbish testing from good testing. And there's a lot of rubbish testing there. The problem of what I call rubbish test is that the value they are providing you are useless, in the sense that there are flaws in the procedure, there are flaws in the sample preparation, there are flaws in the selection of the samples. Those samples that are tested are not representative. But those, if you are not able to actually distinguish if they are good samples or bad samples, well, good test or bad test, you are just going to rely on that particular value because it's a result of a test. The test is always measured. It's a measure, and you assume the measurement is correct. But the question you need to ask yourself is not just if it is correct, it is meaningful for what I need. Now, I'm going to show you 3 different tests that I personally recommend. And tell me if you think which one is good or which one is bad. First one. Oh, by the way, if ever you ask your commission test, make sure that they take a picture of the sample before and after being tested. Okay? That's one thing that you must ask. Your commission test, you're paying, you want it. No doubt. Why? This is DASA. That side is really strong rock. Okay? Right? Is it? QCS 29 MPa. Is a high value or a low value?
Low value.
It's quite low. This side, 111. First test, 29. Second test, 111. Third test, 133. So you go from basically 30 to 130. It's a huge range. Get the same rock, same sample, same block, same coaction. Same drilling. Which one do you use? You're the engineer, you need to pick a value because you want to model eventually. Which one? 30, 110, 130. Which one? Sorry? If you pick a value, you need to tell me not just that, why you pick that. It's the why you want. It's not just a value, it's a reason. Because otherwise you flip the coin and you get the, shall we get the average? The average is what? It's probably 70, 80. Yeah, it's 60 the average. Shall we get that? Sorry? A little bit higher than average is 70? We go? No, 70, yes, 70, sorry. 70. Do we get 70? Which one? Okay, I'll show you again. Number 3, under 33. Number 2, under 11. Number 1, 30. What do you notice? Do you notice anything? Failure plane, what? So, that's good, failure plane. That is why you want to see the pictures. Because the picture are telling you a lot of things. Look at this one. How flat is it? Amazing. It's so cut, pretty much. Right? Look at the second one. Really flat here, and a little bit much rougher here. Look at the colors. You see? It's different color, and this is green. It's really green. Look at this one, the exploding. What is telling you? What are these pictures telling you? They're telling you that this is actually broken through the rock. So this test very likely is a representative of your intact rock. This one is so flat that I bet, actually not I bet, there was a pre-existing plane there that was mineralized but failed along that plane. So this value is nothing else than the shear strength, represent the shear strength of that particular plane. So this test needs to be completely disregarded for basically the assessment of the strength of your material. Right? It's going to be very useful because it's telling you what that particular vein is made of, and what is the strength that you can actually get out of those fractures. But for the characterization of your material, nothing. And then this one, actually this one was positive. It's more positive because definitely this is plain. So and the color tells you that it was sort of a field. So this was a fraction that was already there. But this gray color is telling you that that was intact rock. So that particular sample is telling you something about your rock, and specifically what is the influence of a rock bridge, so a connection of between two sides of a fraction that has not been fully fractured. Okay? So if you need to pick a value, probably you want to use about 130 MPa for the rock, and you're going to use these values to have a better idea of what will be the strength of fractures that have been filled in that particular mass. Okay? Why I'm saying that? Because I really think that is extremely important to start always connecting and thinking about the values you're obtaining and if they're valid for what you do. Okay? Any question? Are you awake? This will be on the exam. Alright? So just to keep you a little bit more awake. Okay. So, oh, it's 12, and here we are, we have another plane. I think we're going to stop here because there's it's a good time, besides being 12, so we are on time. So, to summarize, and then we're going a little bit more into the failure criteria, is that there are criteria, so mathematical idealization of what is happening, and then there is a reality. The two things need to come together, and as a rock engineer, you need to be able to use the common sense, the engineering experience, or engineering common sense, probably, but also the math, and the two, they need to speak together. So the very good engineers, rock mechanics engineer, they look at the excavation and they can already tell you more or less what is happening. Then they do calculations just to verify and better constrain the system. But having a very basic understanding how the math translates in reality is what is going to make you from a mediocre engineer to an excellent engineer. And we are going to keep on doing that till right. Okay. Thanks, and I guess we need to go for lunch and then have a nap. So now, following what has been presented in the previous lecture. So, yeah, you need to test in the lab. At the end, what you are going to have, you're going to produce some plots. And the plots are always under the form of mainly stress and strain. So, the type of test that you have been just learned about, one of those is, there are two that are really commonly used. Are the reaction, the UCS, reaction compression that we saw before, and then extensively the passed out. And then the reaction. One thing I need to mention, and just to clarify, the idea is exactly the same as in solid mechanics. The big difference are two. It's rock, so it's a cohesive material. It's not made of particles that can sort of slide upon each other with some sort of cohesion. So it's basically a cohesive. We are looking at the cohesion and when those materials are losing cohesion. The second thing is that generally all the tests are done dry, so there's no pressure that is imposed, fluid pressure imposed to the system. There are some tests, some material like sandstone, high porosity, where you can actually look at the presence of fluids. But for hard rock, such as granite, dacite, sulfur, you just do that without any fluid inside the system. So, depending on the post peak, you can really transition, as we were seeing before, from a brittle failure so pretty much an abrupt lose in strength, to a sort of plastic to almost a blast hardening behavior. So, and what you can see that in real tests using the same rock, what you can, depending on the amount of confinement you're going to apply, you can really move from a brittle behavior to more ductile and sort of pseudoplastic response. What does it mean? If you think about soil mechanics, it's and you assume that you're failing. The failing, assuming that you believe that it's a more prolonged type of failure where you have a cohesion term that is really a cohesion between different grains and frictional behavior. What you have you go from total loss of cohesion in a very low confinement, and the confinement, what it's doing is allowing to mobilize more and more the friction in between your rock, and specifically in between the interface of the cracks that you're going to produce at the failure point. So, in other words, you can think that the rock will break, but if confinement is there, that confinement will apply some normal stress on the failure plane, and that creates friction, and that friction will appear as a constant stress necessary to produce additional strain in your sample. Okay, so at the end, the cohesion is really helping you in keeping the sample together, even after post-peak, after the peak is the rock is broken. So actually, cohesion is helping you in now having a collapse. That's a problem when you have an opening, because at the opening you don't have any support, any confinement at the surface, and that is where most of the schooling and the rock can fall. But as soon as you go inside the rock, you still have some confinement that will help to actually reduce the damage and how it is propagated. So talking about the polyaxial root reaction is when instead of using cylinder, you use prismatic or cubical samples, and you can apply the three principal stresses independently. And one of the big questions that has been worked and asked is what is the effect of the intermediate stress, so sigma 2. And there's been a lot of work, specifically probably Professor Moji from Japan worked basically the entire career on that aspect. And recently, because of the evolution of technology and the ease of building polyaxial machines that has been pushed in the past, I would say 10 years, there are more and more work that is happening, and so new results will come out. So polyaxial machines are spreading quite dramatically across the globe. But yeah, the sigma 2 has definitely an influence in tends to be positive, so helping the strength of your rock up to a point after that apparently is going to decrease. So, but there's a lot of work and a lot of measurements, and there's still an open question from a research point of view. What is the mechanism of sigma 2 for sigma 2, and how it is helping the strength of the rock? So the other thing that you need to always remember is that Poisson ratio generally are in the range about, let's say, 0.1 to 0.4, more or less, depends on the rock. Those are the values that you can expect. The other thing you need to remember, though, is that Poisson ratio assumes the rock behave perfectly linearly. Then the problem is that when you look at I go a little bit back. You look at, for example, what you measure on the radial strain. The radial strain, you never see really a straight line. This line is almost always curved, while you have sort of a straight behavior from the action point of view. The action strain is linear, the lateral strain is not. What does it mean? That you don't have one single value of Poisson ratio. You have one value at 50% of the strength. So here, you're going to measure your radial strain and you calculate your Poisson ratio. If you pick a different value of stress, your Poisson ratio will be different. So, why I'm saying that? For the simple reason that Poisson ratio is one of the value that is limited in any numerical model, but at the same time is not questionable, but it's very subjective when you are going to calculate your Poisson ratio in a test. So, and that is one thing that needs to be very, very careful. Plus, and I just throw that now, there is another way to calculate the elastic properties of material. So one is testing, this type of testing. The other one are basically using ultrasonic PNS wave measurements. So by doing that, the problem is that you are loading. You know what PNS wave are? So basically what you have a probe on one side and a receiver on the other side. And what you are doing, you are hitting the system with basically waves. Those waves, they go through the sample and they deform the sample. And by deforming the sample, they create a strain. Those really small strain are measured and use those to calculate the GIAN modulus and Poisson ratio. But the problem is that we are working in this area, so a very, very small strain. So again, the dynamic measurements using PNS waves and the elastic modulus and Poisson ratio we measure in the test are really measure two very different strain. So there are I would say relationships that have been developed to actually vary one to the other. But really those are empirical relationships, so you need to pay a lot of attention when you're going to model on what is the value that you are going to take. And for me, the Poisson ratio is always one of those values that is not a value, is a function, and really that is very hard to estimate. And that is basically one number that has you need to have a lot of engineering judgment when you pick it for your models. That is my warning, and that's from experience, or at least. Yes.
There is an accuracy on this curve.
So I couldn't hear you.
So there is an accuracy on this curve.
The radial strength. All the samples I saw, yes. So
why is it so? Why the axial strain is linear and why the lateral strain is not?
good question. And my take is there are several reasons. One is, for example, the anisotropy in your material. The second is is the heterogeneity, of your material. And generally, and way you're using to measure the radial strains, there are several. So depending on if you use a radial chain, so a chain around and look at how it elongates, that is an average. Probably that is one of the best way to do. Others are using strain gauge. This is actually a strain gauge. So it's more a point, and you hope that when you touch the strain gauge is the right point. Very likely it's not. And so far so on. So there's a lot. To measure the Poisson ratio, it's extremely difficult. And to me, experimentally, I always have a problem. So you have a range. So again, we need to start thinking about not just one single value, but a range of values. And if you do more testing, because you need to have more testing, because the one sample is not representative, you need to make sure that you have enough. Very likely, you are going to have a range of values, and it's not for sure you want to use the average, because the average doesn't really tell you much about the failure. That is actually what you're looking for. So maybe you want to start looking at the extremes and see really what is the variability or the sensitivity of those values on your design. That is one thing that you always start thinking about. So we already said about the Brazilian test, so this is basically what is happening. One caution is that failure must start from the center and propagate towards the platinums. So if you get a failure path that is like that, it's not bad. If you have a shear failure there, it's not a valid test. So, and there's a lot of, it's actually a challenging, seems a very simple test. And it is a very simple test, a very easy, a simple wrong test. In the sense that there's a lot of precaution you need to take for Brazilian test in order to get it right. And there are assumptions, and the assumptions are the fraction must start from the center of the disc and propagates towards the lattice. And it's so fast you cannot see, so you need to look at the surface after and make sure that that surface very likely meets the expectation. If it's not, you are said to discard that test. So one of the big problems that we recently found, and just to share, is that instead of having a platen that way, if you have a platen slightly oblique, what it means is that your loading axes are not really meeting at the center. That is going to create a big problem because apparently the samples seems right, but in reality the results are wrong. And what you're going to obtain is something like that. A failure that doesn't start from the center, starts from somewhere there, and propagates towards the flatlets. So it's extremely difficult to actually identify. But we will be noticing some of the samples in one particular machine that we have, and that's actually the explanation. The two loading platens are slightly non-parallel, and that non-parallelism is actually giving us a problem in the results. So again, observing the test is going to give you the much more confidence in the results of that. So, what do you do with the triaxial test, the vector triaxial test? Well, and you use the uniaxial test and Brazilian or direct tensile. What we're going, we can plot them on shear normal load, normal stress plane, And what we can is basically look at what is the envelope that can be built using those more circles that obtained from your reaction test and QCS and tensile test. And those will, if we assume the failure obeys to the Moore-Coulomb criteria, so it's a shear failure, you can calculate what is the cohesion and the internal friction angle of those particular centers. Okay. So really, and those two parameters, C and phi, are really, C as the cohesion, phi is the friction angle, internal friction angle, are again important because most of the numerical models are using a Moore-Coulomb failure criteria, and those are the values that we need to estimate. So again, there is few issues. So again, as you were told before, well, there's a huge range in values. For example, UCS, limestone can go from a very weak to a really strong one. So limestone doesn't mean much, but it's really the type of limestone you're dealing with is what you need to refer with, and will reduce actually the range. But there will be always a range of values. Tensile strength is again huge range. What you need to know is one thing, very simple, more or less just a rule of thumb. Tensile strength of a material, of a rock, is about 1/10 roughly of the compressive strength, more or less. But that is the ratio. Of course, you need to measure those, but you can assume that it's about 1/10, 1/9, something like that. But 1/10 is a nice number, so you just for your rough calculation, use that. Okay. So point load is a very simple, and you saw machine before. The figure of machine a point load. Okay? Point load means that you saw rock, get your foot. Put the finger like that. On the side. On the side. Press it up to break. That's the point load. So you fail by basically pressing 2 points of your material across, along the same axis. That will create a failure. That failure is then empirically correlated to everything, from porosity to strength, tensile strength, compressive strength, and there is a joke in our lab that you can actually use the point load to do everything, even understand if it rains tomorrow or not, because there will be a correlation. So again, point load is actually a very useful test, especially because it's quick and can give you the range. Pay attention to the correlations, and if you're using them, make sure you go and read the reference, because there are always very fine printing of those correlations that tells you where the correlation is valid. So don't just use an equation, read the paper from where it is coming from to really make sure that you understand if you can really use that or not. And again, correction factors. Again, these are really correlations. Fracture toughness is another important parameters, and this is very important, especially for the numerical model, the advanced one that we are going to see later during the course, specifically with the FDEM, finite discrete element modeling, IRASU specifically, where it's a fracture mechanics code applied to rocks, where you need to propagate the fraction. And the fracture toughness is basically a way that measures how much energy you need to put in the system to propagate the fraction. Now, just two things, one thing. We're going to talk about mode 1, mode 2, mode 3. So mode 1 is a tensile fraction. So you break your sample by pulling it apart. Okay? Mode 2 is a shear fraction. So the movement is along the plane. And mode 3 is basically tearing. So you have a rotation along a vertical axis. Okay? So these are the three three different mode of failure. And mode 1 is tension, mode 2 is shear, mode 3 is tearing. Now, these are macroscopic type of failures, and each of those is associated with the fracture toughness. Now, fracture toughness is relatively easy to measure in mode 1. It's impossible in mode 2 and impossible in mode 3. Despite people are claiming that it's possible. Now again, me, opinionated, mode 2 does not exist, and microscopic relevant, it's only mode 1. It's just only a tensile displacement that creates tensile failure that is happening. However, you can have a shear displacement that is superimposed to that tensile movement that is actually made to appear that the shear failure is happening. But the rock, that's not just me, but I'm clearly saying that very loudly, fails in mode 1, and mode 2 is just kinematic because of the loading condition. Okay?
Many ones say that they have fabricated mode 2.
Yes, but I can tell you what. So, mode 2 measurements, according to the ISRM, you have a sample that is actually this way. So basically, what you have a sample, well, from the top, horrible drawing. So this is a rock, and that is cored, and is cored up to a point, and then same thing on the bottom. And what you have, you push here and you react on the external. And what they're saying is that you create a shear failure here. Model that and look at the sample. Failure will start from here and go there. From here, go there. How is it working? So if we do that, you push. Basically what is happening is that you have a tensile, all this is open. So it's basically a tensile stress that will initiate the fracture, and then the stress will rotate and will jump. It's always like that. And you can model, it's very simple. Despite that, they claim, or they accept that this is mode 2. To have a successful test, you need probably 15 of those tests, and you might be able to claim one successful. I personally don't trust them. Say that macroscopically shear mode exists because definitely you have displacement along those fractures, but that is a coalescence of very small tensile fractures. How you deal with that? Well, you do a compromise, you sort of accept mode 2, but I still don't
Many
like
groups are also claiming that they are going to produce mode 3 then.
Good luck. So again, it's me. Say that KIC is the fracture toughness in mode 1, K2C is a fracture toughness in mode 2, and K3C is mode 3. Well, again, I'm telling you that mode 2 does not exist. Irazu has a mode 2 failure, and for simple reason that you can model the rock at so small scale to really just use mode 1. So you need to account for those apparent shear failure. So you need to compromise on what you want. Okay? So, but be very, very careful when someone claims that you can measure K2C in the lab. Okay? Other physical properties. Well, these are really like soil. Yeah, the density, the porosity, water content, all those are existing. Porosity for rocks, igneous rock are very, very low. We're talking about, about 1 to 2% maybe, but can go up to 30% for some sandstones, so huge rocks. One thing that talking about innovation, talking about analog materials. Right now there is also a new trend. There's a few things that are coming to rock mechanics. One is artificial intelligence and machine learning, and I think we will learn about at some point. And the other one is 3D printing. And you can actually print rocks. You can reprint particles, you can use quartz, you can use whatever is the material you want, as long as there's sort of an equal distribution of particles, and you bind those together. And you create rock that you can actually design the computer, send to the printer, and you get your sample that you can test. So again, those are very useful if you want to sort of try to create a homogeneous material where you start measuring some of the properties that we were talking about. Density, well, density again between 2.5 and 2.8. 2.7 is a really nice number that most of the people used. And the other thing is that hardness is it's another aspect that you need to measure, especially when you need to actually break your rock. And well, speed diamond is one way to measure it.
In our coal mining, it is very important for cutting the root cause.
Yeah, exactly. So you need to know, because basically it tells you what is the tool that you need to use to excavate, if it is a mechanical excavation. The other thing that is it's really important is the abrasivity, because you want to break the rock, but you don't want to consume your tool too quickly. So, and the abrasivity is there's basically only, to me, to my knowledge, is the Scherzer test that gives you an index that is related to the abrasivity, and is a very tedious test, because what you have a particular puncture, so with a 45 degrees angle, and you slide at constant velocity for 1 centimeter on your rock under a specific weight, and then you take it, you go under the microscope, and you look how that 45 degrees has been changed. You measure the length, and that will give you the abrasivity index. Okay. But that will tell you what type of steel or material you need to use for your tools. And this actually, from a cost and operational point of view, is extremely important, because it also tells you how often you need to start the machine, TBM for example, diamond boring machine, to replace the cutters. And that is a big cost, and this is one of the parameters that goes into the design of the machine and the commissioning of the machine. And you make a mistake there, actually you're going to pay that for the entire cost of the project.
Big mining machinery, they are very much easy.
Yeah.
Surface miners, continuous miners.
But I can tell you one thing. One of the it was for a little bit the longest tunnel in the world. It was the Leuchberg in Switzerland. It was 54 kilometers, I think, long. No, in hard rock. overburden over 2,000 meters at the highest. So what they screw up a little bit on, sorry for the recording, they didn't account too much for the abrasivity, and what was the problem was the cutter. You know what is a cutter? Do you know what it is? No. Do you know what the TBM is, tunnel boring machine? Okay, tunnel boring machine is a big drill, 13 meters, maybe 12 meters diameter, so 4 stories high, okay? And that machine is basically rotating and drilling the mountain. So the drill is made of this big disc, 12 meters diameter maybe, and there are the small discs that actually impact, rotate, and breaks the rock. Okay? Those are really the cutter. So this big, very heavy, and very strong. The problem was that for the Leuchberger, they didn't account for the very high abrasivity of the igneous rock there. And what happened was basically they were flattened. And by being flattened, by being abraded too much, they were not rotating anymore. They were sliding, they were not breaking the rock anymore. And they had basically to stop the machine much more often than what they were designed for. That added probably about a year, I'm guessing about a year in the project, cost of the cutter and so on. So this is a really an important parameters that should be accounted for. Just some ranges of those properties. Permeability, well, permeability we're going to talk a little bit later on, but it's basically how much flow can go through that material, and is always used the equivalent Darcy law approach. Okay. Wave velocity. So okay, wave velocity are actually quite important because is telling you one thing that is actually very important is a proxy for the presence of cracks within your rock. So generally you can think about sort of range between 5,000 7,000 meters per second for a igneous rock, and we have an expert there that can probably give us better ranges, and it's a little bit slower for shale, sandstone, conglomerate. Why? For the simple reason that you have more void, so the wave does not propagate as fast as an intact material and compact. Okay? Now, one thing that you can think about doing in the lab, and concrete people do it all the time, is actually measure the P wave, pressure wave, in the sample before testing. You measure that. What is happening is telling you that you know that if that is a compact material, you have, let's say, 5,000 meters per second range. Now, you have the same sample and you get maybe at 3,500, maybe at 2,500 meters per second. What is telling you? It's telling you that probably there's some cracks there that you don't see, but is present. So it's telling you what is the state of your sample before testing. So you can start counting. And even better, you can measure those in the three axes or several axes, and you have a feeling on how homogeneous that material is. Okay? And this is really important for a material like shales or gneiss, where you have some sort of beddings, some sort of sorry? Foliation for gneiss. So where you the mechanical property changes, and you should be able to sort of have a feeling of how an isotropic or transversal isotropic the rock is by just looking at this value. And it's 5 minutes, as long as you have the system. And of course, there are some correlations that, as I was saying, you can correlate these to shear modulus, Poisson ratio, and the elastic GIAN functions. So now, what we have all is mathematically what we want, and I'm sort of jumped ahead already. You want to correlate the stress you apply, the strength of your material. So, and basically there are yield strength criteria that are being proposed. Probably the most used that has been taken directly from soil mechanics is the Moore-Coulomb criteria. And the Moore-Coulomb, remember, as one is valid as long as your system fails in shear. So it's a shear criteria. You assume the failure is along the shear plane. And the shear plane will have some cohesion and some friction. So that was developed for soil and was being used directly for rock. Okay? Formulation? Well, basically that's the equation. This is one equation that you should remember. I think you did that in high school, I believe. In physics, I think, maybe even in middle school. And the end is that shear is equal to the cohesion plus the normal stress times the tangent of the friction angle or the friction coefficient. Okay? Tangent friction angle is the friction coefficient. That's pretty much what it is. And assumes that the failure happens along a straight line. Now, few equations will maybe remember. But when you look at the Moore circle, the plane is defined, the failure plane, by theta, and that theta is basically 45 degrees plus half of the friction angle. Okay? That is something you need to remember. Because that will also give you very nice way to see if what you are doing, especially in modeling, makes sense or not. Okay? Very often you run the equivalent of numerically, you can run a sample that reproduces, let's say, triaxial test or compressive test. You know what you're going to have? You're going to have maybe development of something like that. That is your failure. That is the sort of the red area that corresponds to where the sample will fail. Okay? That is what was those nice pictures of models. I hope you have seen them somewhere on papers. Right? Does it make sense or not? Is it correct or not? How do you judge that? Well, look at the parameters, and you have your phi is equal to how much? Say 30 degrees is always a nice number. Okay? I know that. So the model is actually doing what I'm expecting from the model. But You can go online, there are papers where this angle is 45 degrees. What does it mean? 5-0 means that we are running a frictionless model. Does it make sense? No. So, again, what I'm saying here is that by understanding what are the principles behind, for example, the Moore Coulomb, you can use those to quickly check if the model that you are running or someone else is running makes sense or not. And generally, in complex models, numerical models, you do have a way to estimate very quickly, evaluate very quickly if the model makes sense or not. Okay? It's a very simple, I would say, trick. And you can impress a lot of people, really, because it's something that many people don't think about. Like, check it. It's a good thing. So, and yeah, well, that is basically most of the models have a tensile cutoff, and it's about 1/10 of the UCS, the sigma C, and that is again is the fact that that line will stop before touching the axis of sigma. Okay, so basically your Moore Coulomb or Raux is pretty much there. Okay, as a tensile cutoff. That's the easiest way to implement that. Well, some more equations that you don't will be provided. So, again, that is extremely widely used. But one of the problems really with the Moore Coulomb is that assumes the fraction to be the failure to be along a shear plane. So it's basically a shear plane. But it's not the case, for example, along excavations, where it's not really shear failure, it's more a tensile crack that develops. And that is where the Moore Coulomb falls a little bit apart. So that is why quite a few people started looking at the Griffith Theory. And Griffith Theory is looking at what is the stress necessary to actually propagate a crack, pre-existing crack. So you have a penny-shaped crack, and what it's doing, you can define what is the stress at the tip, and when that stress at the tip overcomes the strength, the tensile strength of your rock, that crack will propagate. Okay? Extremely used. And everyone uses that equation without really looking at what they said exactly. So very exciting. So I just wrote that. One of the problems of the Griffith Theory is approach is that the stress at the tip basically reaches infinity. And that's a problem. And according to Barnablat, unfortunately most of this work in Russian, so I never really read the originals, but just a summary of what he was writing, is that actually he claimed that Griffith made a mistake in the derivation and actually is not infinite, but is a little bit different. So if you're interested, Barnablat is a Russian mathematician that ended up as a professor at UC Berkeley, and sort of in a very direct way was pointing at the mistakes on this particular criteria. Despite that, Griffith strength criteria is quite widely used still in rock mechanics under this formulation. And and what it says is that the crack extension is always about 8 times the uniaction tensile strength. That is pretty much what this criterion is assuming. Okay, and those are the type of formulations. The interesting part is that with respect to the Moore Coulomb, that is a linear criterion, is non-linear. And that is matching much better what are the experimental envelope that you can build from numerical text. So, but it's limited to really low confinement, and specifically it's good when you don't have, you have low confinement. High confinement is not working very well. So building on the Moore Coulomb approach and on Griffith theory, Oak and Brown came up with a really empirical strength criteria that put everything together and appears to be something like that. With M is a function of the rock. So what is the advantage of Oak and Brown is that they extended this approach not just to the intact rock, but to the rock mass. And by relating what is the large scale to the response of the material and to a rock classification that we will see tomorrow, I think, became a very useful and widespread strength criterion for specifically rock mass, because it has a classification and also a number that can be directly used in numerical model. And that was really the big, I would say, contribution that they made. So going back to silver rock, M has different values depending on the rock, and generally you calculate that from laboratory test as a back analysis. So basically it's a thinking pattern, if you wish. So, and the way they did, they look at a logic test, there's a point cloud, and they fit an equation that sort of goes through that point cloud. So it's not perfect, it's not bad, and gives you, with the uncertainty, at least a good starting point. And again, you're not using just one value, you tend to use a range always. So, and when if you ever have the chance to meet Oak, one of the things that he always says is claiming that sometimes he says, my worst mistake was to actually write the Oak and Brown failure criteria. For a simple reason that people are misusing that. They don't understand that you should have a range, not just one single value. If you miss that point, you haven't read my papers, and you don't understand at all what rock means. I'm a little bit exaggerating what he says, paraphrasing what he says, but the meaning is really you need to use a range, you need to put your engineering thinking and understanding and common engineering sense into the use of this type of approach. You don't use the comma, you use actually round to the 10th. Okay? Now, I don't remember anymore. I thought that we should finish. 4:15, so okay. Now, we've been talking about the single rock testing. But the reality is that we might want to measure, to design big slope or a tunnel. And one of the challenges is that the rock is not in as fractures. And even in the test I showed you this morning, there was that plane that screwed up our calculations and gave us a very low strength value. So, but that was not just the unlucky sample. It's sort of the standard type of features that are always present in your rock mass. So actually it's the other way around. The intact non-fractured rock is very rare and almost impossible to find. There are very few sites that can claim to have this rock mass with pretty much no fractures. So it's actually fractures are there all the time. However, depending on the scale that you are going to design, the scale of your structure, you might actually use not encounter any fractures. You might encounter maybe only one joint, maybe just few joints, maybe more, or maybe so many that actually your entire volume of rock is equivalent to a soil, an uncohesive soil. Because it's so large and the blocks are so small with respect to the dimension you're modeling or dealing with, that those are basically small blocks, small grain of sand equivalent. Okay? So depending on what is the scale you're going to actually engineer your structure, you might really want to use either one or the other approach. And so you might want to use the strength criterion for intact rock or the one for the rock mass and the other side. Okay. So again, Oak was very concerned about the misuse of his work, came out with sort of an applicability. So again, make sure that you are using in an appropriate way the different criteria that are available. And that's really important because you don't want to misuse the tools that you have been given. Okay? So that means that for the same slope, depending on what you are doing, we're dealing with a borehole of 10 centimeters, well, probably it's quite possible that you don't encounter many fractures. You might want to use the strength criterion for intact rock. A tunnel of 12 meters, probably you're going to encounter quite a few joints. So depending on how fractured is your volume, you might use something specific. But even with all that, there's so many features there that definitely you need to account for them. And probably you want to use some sort of O'Brien strength criterion for options. Okay? How are you doing? You need a break. So let's have a break. So the scale, just to conclude, the scale is actually very important. And the scale of your infrastructure needs to match what the tool you are going to use. And there is always this scale effect that is really embedded in rock mechanics, and you need to start knowing how to deal with it. How you're using or upscaling the value that you can obtain in the lab to a scale of a mine, to a scale of a reservoir, to a scale of a tunnel. Okay? And there's a lot of thinking that goes into it. And before I finish, before we break, one key aspect is, it's actually my passion, are the fractures. So fractures is really what distinguish the intact rock to the rock mass. how many fractures are there, how they are oriented, how I can incorporate their effect in my design is the key for an engineer to be successful in their design, in his design, their design. Okay? So let's have a break, and then we go a little. So, how are you doing? Are you awake now? A little bit? Stop. So, we are set to have a tutorial now, 2 hours. Tell you the truth, I want to go to, I would prefer to do something different, to completely change, despite our really nice organization, and continue just to tell you a little bit more about the fraction, because I think that this is going to be really useful for tomorrow's sessions. And what we are going to do on principal stresses, I think we're going to do that on Wednesday. So I'm not sure if you do have a computer with you. What I'm planning is, have you ever heard about the software Examine 2D? So Examine 2D was actually it was a master thesis software developed really long time ago. And
if you all have your laptop,
yeah, it's a very simple boundary element software. It's extremely fast. It's basically was distributed for free for this type of occasion by rock science, and was developed more than 20 years ago. But still, very fast and gives you a very quick solution, elastic solution of basically the stress around the excavation, and it's almost real time. So what I'm going to do, my plan is give you the software. You can decide to install on your computer or whatever. And what we're going to do is just to look at a few, little bit how the stress changes with the direction and the magnitude with respect to excavations. And again, as a first solver is a very nice way to have an idea of how the stress state will change with respect to your particular problem. Okay? So now I'm not sure if it's going to be at a USB or you're going to get a link to download from the cloud. And that is sorry, USB. Okay, it will be at the USB. So, and it's basically it's up to you to do whatever you want. Play with, learn more, or learn less. It's fine. But we are going to briefly use them. What I would like to go today a little bit more in depth is what is really the role, we had a brief discussion before on the heterogeneity or inhomogeneity of the rock, and specifically also on the presence of planes of weakness. So you already heard before that the rock is, I think you are aware if you are here, rock is not homogeneous, it's completely material and is made of different minerals. The bonding between these minerals has different strength properties. There are pores, there are micro cracks. It's just It's not nice homogeneous material at all. And it's not continuum at all. So we can, so far, we've been sort of assuming that it was homogeneous and continuum, but the reality is not. So we're using assumption like example 2D will do, that is a homogeneous linear elastic material. That will give us a very quick first guess or idea of what is going to happen. But the reality is that the rock will behave a little bit differently, sometimes drastically differently, with respect to those simple models. Okay? That is one thing that is, again, it's, I hope one of the notion that you take is we have a lot of simple tools. We are using them, but we need to use them with our brain on all the time. We don't have to accept those. We need to use them and understand what are the boundaries where those tools, like example are active. And that is actually very important. And the problem is that sometimes you trust so much on those models that suddenly you don't believe anymore what the rock is doing. It says, that's rock. The rock is wrong. My model is right. And that is where you should really stop doing your job and just do something else. Or go to sleep and realize that actually the rock is always right. And probably is your model that's not correct enough. And by the way, it happened to me even last year. Someone wanted us to force the rock to behave according to his model. And it was not. The rock was behaving as was wanted. So that is one thing that you need to be aware. So the rock mass is something like that. This is just a nice picture of how the rock could be. And it's not homogeneous. And very often there is these fractures, bending planes, schistose planes that create an isotropy, not just on, for example, on the sonic velocities, especially, more importantly, probably, on the mechanical response. So, bending rock, depending on the angle of loading with respect to the bedding, will be different. So, would be if sigma 1, so your loading in this case is parallel to the bedding plane as a bed. If it is perpendicular, no, actually here, sorry, let's define the angle. So these are the bedding. This angle is your how is it called? That's called alpha. Okay. So what he's saying is basically is that when you test your rock at 0, you have a value. Between 45, you have a minimum. And when you test that and parallel to the value, you have another value. Very often what you observe is this value is higher than that one. So it means that this condition is generally higher as a strength with respect to when you load parallel to the value. But what is important as first approximation, you can assume this is the same, And what we can assume is that you have some sort of this type of strength distribution as function of your angle. Okay? So what does it mean? It means that depending on what is the orientation of the loading with respect to the bedding planes, you are going to have a different response of the rock. So the orientation of the rock will fail more easily than others. Okay? And that is actually very important, especially when you are designing an excavation. Okay? So basically, what is we are saying is pretty much this one. So you have 0, and at the incline, you change your strength, but you also change the way the rock breaks. So in this area, in the flat, you really fail the material. Then here, the presence of your weakness plane is important, and that is where your failure is really dictated by the weakness of your pre-existing plane. Do you remember the test that failed at 30 MPa today that I showed you this morning? Do you remember that? Pretty much, we were loading exactly this area. I had a plane, failure plane, pre-existing plane, and it was really failing. You can see that there's a big difference in strength. So when you are dealing with a rock, especially with those sedimentary rocks, like shale, right now gas shale, really big, unconventional oil and gas are all in embedded rock. Those are really you need to account for the presence of these bending planes and the orientation with respect to your loading when you're going to engineer them. So another aspect of rock mechanics that is very important and was mentioned before was, for example, for nuclear waste industry. So nuclear waste needs to be disposed in some way. Underground is a very safe place. In many countries, such as, for example, US, and especially France and Switzerland, have decided to put them in sedimentary formation, where the bed is actually the weak plane, and they do need to account for them in their design. So it's really something that is important. Just what I was saying. We can skip these things. So I just skip that. So now that's pretty much what I want to say. Now, fractures, bending planes. So these are really the presence of these bending planes, the presence of joints is it's really what makes rock mechanics interesting. It's not a boring material that always behaves as we expect. It's really something that changes all the time, and specifically with the conditions, with how the rock organizes. So there's not one rock equal to the other. They might be similar, but they are different. So one of the things that we really need to do is to characterize and account for the fractures, for the bedding things. So and that is it's one of the things that is always a fashion. Shear strength of rock joints, roughness, so far are parameters that if you really Google and look how many papers have been published and are still published, it's just an ongoing direction of research since the 1960s. It's just crazy. It's all the time. It's always how do we account for the presence of the fractions. So, now, when I was doing my PhD a couple of years ago, I was actually tasked to work on fractures, and I had no clue why. I was feeling was just boring. I said, well, I've already done that. Okay, let's do it. It took me actually only at the end of my PhD I would start understanding what the hell I was doing, and it was during the first postdoc I did that I started realizing that actually it's right there, very important. And they need to be accounted, and under really understanding how the behavior of a joint or fracture is, what is its influence on the response of the rock, it actually makes a big difference from a good interpretation, a bad interpretation of your rock response. So, and the other thing I really would like to pass to this crowd is my experience now is, well, actually not a couple of years, just quite almost 2 decades ago, on my continuous work on joints, and specifically on how we can characterize the fractures and how can we account for them in our engineering activities. So, because of that, I will kidnap the tutorial time to deep into basically what I learned, and I hope I can pass some of those to you, at least a few points. We are going to have a break at some point soon, because otherwise I know that we are going to fall asleep as summer is doing already. But I know that everyone has been traveling for very many hours. I thought, by the way, I was the one that was coming very far away. That's distance, yes. Time-wise, I was just, there was a piece of cake that I have with respect to someone else. So I'm really happy that most of you are still awake. So,